assuming a general solution of the form y is e to the lambda x, then you only have one solution, e to the lambda 1, which is equal to lambda 2. To obtain the general solution, I believe Ms. Chagpa took you guys through the procedure of, there is what we call reduction of formula, reduction of order. So if you follow the steps, you arrive at the second solution. So thing is, you take the only solution that you have, which is e to the lambda something, multiply that by a constant, which is not a normal constant, but a function of, if your solution is y of x, then you're multiplying it with a constant which is a function of x. Say u of x times the solution you had, then check what u of x need to satisfy for it to be a solution to the differential equation. We apply a similar technique. So when p is not an integer, you let some function u of x times jp of x be a solution to the differential equation. The differential equation in this case is x squared y double prime of x plus x y of x prime y of x plus x squared minus p squared y of x equals 0. So if you let u of x, jp of x be a solution to this, in other words, you are saying your y is equal to u of x times jp of x. If a function y is said to be a solution to a given differential equation, then if you plug in that particular function together with its derivatives, it should satisfy the differential equation. So our differential equation has y double prime, y prime, as well as y. We have y. We can obtain y prime as well as y double prime. If we differentiate y, we get y prime. If we go ahead and obtain the second derivative, then we get y double prime. So let's do that, then plug into our differential equation and then check what needs to be satisfied for this to indeed be a solution to this differential equation. So if y is ux jp of x, y prime is the derivative of ux jp, but you notice that this is a function, it's a product of two functions, so definitely we have to apply product rule. We'll get d dx of the first function u times the second function held constant, plus we differentiate jp holding u of x constant. If you differentiate u, you get u prime. So this is u prime jp. If no confusion arises, we can just write u and j, but having in mind that both are functions of x. Plus differentiate j sub p, you get j prime p times u. This is our y prime. We need the second derivative. Y double prime will differentiate the first derivative, so we'll get u d dx of u prime jp plus d dx of j prime p. Again, they are both products of two functions, so we apply product rule to each part. If we apply product rule to the first part, what do we get? You can first differentiate u prime holding jp constant, then differentiate jp holding u prime constant. Go to the second term, differentiate j prime sub p holding u constant, then go ahead, differentiate u holding j prime p constant. If we differentiate the first term, what do we get?
U double prime jp.
U double prime jp
Plus u prime jp.
Prime. Right?
Yes.
We differentiate the second term.
J double prime u. Jp double prime u.
Oops, this is supposed to be j prime p. So the third term is j double prime p times u plus
jp prime u prime.
Are there any like terms that we can combine? Any like terms?
U prime and J, U prime and J prime.
So plus 2 U prime J prime P plus J double prime sub P times U. So next thing is we want to insert this into the differential equation. You can say inserting y prime and y double prime into the differential equation. Remember the differential equation is x squared y double prime. So we have x squared times our y double prime is u double prime jp plus 2u prime j prime p plus, what do we have? What is this term?
JP double prime U.
Plus x times y prime. So x times, what is our y prime?
U prime JP plus J prime U.
U prime jp plus j prime u.
Yes.
Plus x squared minus p squared times y. Y is uj jp. Let's distribute the x squared in the first bracket, distribute the x in the second, and then distribute the ujp to the third bracket. What do we have? Should be easy to see. X squared u double prime jp plus x squared 2u prime jp prime plus x squared x squared u, is it j double prime p?
Yes.
If we distribute the x, yeah, this one I can see, plus x u prime jp plus x j prime u plus x squared u jp minus p squared u jp equals 0. Forgot to put an equal to 0 here. Let's combine j double prime, j prime, and j. Terms with j double prime, j prime, and then j. If you extract those three terms, what do you have? We want to isolate those terms because jp is a solution to the differential equation. We just went through that. So if it's a solution, if you have its second derivative plus the first, x squared times its second derivative plus x times the first derivative plus x times j, we need to set that quantity equal to 0. So what do we have? I don't know if you get what I mean. If a function y is a solution to a differential equation, then y prime, y prime, y double prime, if you plug in those derivatives, it should satisfy the differential equation. In other words, you should have the left side being equal to the right side. So here we are having some j prime, we have a j double prime as well as j. If we can isolate those terms, x squared u j double prime p plus x, where j prime p times u plus actually we have x squared minus p squared u times jp. This term, and this term. X squared u jp prime. U is common. X squared j double prime p plus x j prime p plus x squared minus p squared jp. U is common. We have u outside. If I say that the whole of this quantity is equal to 0, do you guys get it? The Bessel's differential equation takes the form x squared y double prime plus xy prime plus x squared minus p squared y equals 0. But here our JP was found to be a solution to the differential equation. So JP is our y in this case. So we have an x squared JP double prime plus x JP prime plus x squared minus p squared p JP times u, where JP is a solution. So do you agree that the whole of this will go to 0?
Yes.
So if these three terms, if the sum of these three gives you 0, what terms do you remain with? We need to set the remaining terms equal to 0 and then try to determine what our function u needs to be. What do we have? Or maybe I can justify that you say this, since j sub p of x is a solution to the Bessel's dE. Maybe you guys are just tired. What terms do we remain with?
X squared u double prime jp plus 2x squared u prime jp prime plus x u prime jp
Equals 0. For you to proceed from here, you need to divide through by I thought Mr. Nonda went through this. X squared u prime jp. Divide through by x squared u prime jp. So this implies you will have x squared u prime jp divided by x squared u prime jp plus the second term is 2x squared u prime j prime sub p divide by, we are dividing through by x squared u prime jp plus the third term is x u prime jp. We divide this by x squared u prime jp. So dividing through, what do we get? In the first term, u prime jp will cancel out. This is supposed to be u double prime, right?
Yes.
yes
So if we divide through, what do you get in the first term? What cancels out? What do you remain with? X squared, of course, cancels out. JP. This cancels out. This cancels out. So you end up with u double prime over u prime. Plus, what do you have in the second term? Batman. But the 3 minutes.
Have 2 j prime over jp.
JP prime over JP plus 1 over x, right? No, it's charged. It's fully charged. Don't connect it. Equals 0. From here, we can write this in terms of the derivatives using the natural log. d dx of natural log of some function g of x is g prime of x divided by g of x. So if I argue that my u double prime over u prime is equal to d dx of the natural log of u prime, is it okay? It is,
Yes.
right?
Yes.
So if you use a similar approach, tell me what to write in place of the second term. So this will imply d dx of natural log of u prime plus d dx of natural log of j p, right?
Yes, but these are 2.
Plus 2 times d dx of 2 times natural log of p plus the last term d dx of natural log of
X.
natural log of x, correct. This is equal to 0. If we factor out the d dx, natural log of x, natural log of u prime plus 2 times natural log of jp plus natural log of x d dx of using laws of logarithms. What do we do to the functions?
We multiply.
So u prime times, we are supposed to apply 2 ln jp is the same thing as ln jp raised to power 2, right?
Yes.
So we multiply with jp squared times x equals 0. You guys supposed to be having another class right now.
Yes.
Yes, you have a microwave class.
Okay. Naona wengine hapa wanajua kusoma time, washaweka TV because I told them 11 watawatch. Sasa we can just stop there. Tangu nikubaie watch unajua kujisomea time. Hey, Jaber.